Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff, the very good stuff. And I am super happy to have Artemi Camps-Fariña with us today. Hey, Artemi.
Hi, Frank. Thank you for inviting me here.
Oh, well, thank you so much. We have a little
I'm good.
We got a little bandwidth lag, so we got to be a little slower on the responses, but it's all great.
Kind of far.
Artemi, where are you located at?
I'm currently at Madrid, in Spain.
Very good. Very cool. So we are third of the way around the world as we do this one.
Yes.
Very good. Let's see, and it is October 10th as we record this, and is fall on the way in Spain yet, in Madrid?
Oh, yes. It actually just started raining right now.
Ooh, wow. All right. I'm in Phoenix. There's no rain yet. We just did our rains. Summer is when Phoenix gets its rains, but we've definitely turned the corner, and things of moving toward the fall. So it'll be pretty cool. And what is your position there in Madrid?
I'm currently a postdoc.
Cool. Very nice. Very good. And you got some nice scribbles over your head there. That looks appropriate.
Yes.
Astronomy-ish there.
It's actually theme appropriate. This is kind of an outline for a chemical evolution code.
Ah, very cool. Nice.
Yeah, it's chaotic as I am.
Now you got to do is implement it into some source code, and away you go. So
yeah, well, someone who knows more about coding will do the hard work, but have the requirements that this is what it needs to do.
Good. And this is what we want out. Yeah, it's very cool. And so that chemical evolution must be related to something that you like to do for research. And so what do you like to do for research, Artemi?
Well, I'm mainly interested in galaxies and how they evolve over time to get the current form that we observe. What are the processes that drive it? What are the ingredients that you need to recover a galaxy as it is today?
Cool. Very nice. And that is going to bring us to this very awesome APJ article. It's open access, people. Go ahead and grab it for free. Go get it. The chemical evolution history of MaNGA galaxies. And Artemi, take us away.
Thank you. So first of all, I wanted to give a nice shout out to all my co-authors, which helped me quite a lot to get this article because it has like a ton of figures, like Frank knows, like 30 or 40, and a lot of information really. And the main idea is to measure the chemical evolution history of galaxies using a large sample such as MaNGA. And we focus on the chemical evolution because so many of the processes that drive a galaxy's evolution leave chemical imprints on the galaxies. As such, if we know the chemical evolution of a galaxy, we have strong clues about how it evolves and the processes that drive it.
Cool. Yep.
And for those who maybe are not as versed in the chemical evolution of galaxies, the main idea is that when stars are formed in a galaxy, they start to die progressively depending on their mass. And when they die, they liberate some metals, as we say, that become, if anything, heavier than helium,
you can say
into the interstellar medium. And this is the metallicity of the galaxy that we use that we are measuring here.
So you're measuring gas phase abundances?
Not really, not exactly. See,
okay.
I'm kind of cheating here.
We'll get there.
Yeah, that's a good question. Because if you measure the gas metallicity, you can only measure it at one time, as you see it. I'm taking advantage of the fact that when stars are born, they're born with the composition of the ISM that they are born in. So if you can measure the abundance of the star, you know the abundance of the ISM when the star was born.
Good.
If you can then age date that population of stars, you can assign the abundance at a particular time in the galaxy's history.
Yes.
And that's the basis of the method that we use to measure the metallicity over time in a galaxy.
Okay, I'm with you.
So we are measuring the abundances of the stars but we're using that as a proxy of the abundance of the ISM, of the gas phase, when they were born.
Cool.
And well, one of the main things you need to keep in mind is that this is complementary to the other method that is typically used to measure the chemical histories, which is cosmic surveys. Basically, you get your big telescopes, you observe faraway galaxies, and you measure the gas phase metallicity on those galaxies.
Got it.
They're not as much competing methods as they are complementary methods because they have opposite problems.
Yes.
The problem with gas phase metallicity is sample. You lose completeness of the sample the farther away you go.
Yeah.
Higher redshift, you're selecting for bright galaxies, high mass galaxies. With my method, I can get the histories of local galaxies.
Cool.
I observe a galaxy right next to us, and I know how it is backwards through time.
Okay, I'm with you.
So, but the problem with the method I use is that it gets less reliable the farther back in time you go, as you might imagine. And there's a few like method dependencies, degeneracies and stuff that are tricky to deal with. But really, both of them have opposite problems. With cosmic surveys, the robustness of the method is always the same because you're measuring the strong lines and those are the same no matter where. But you have a worse sampling.
Yeah.
My method, the sampling is perfect because it's even the same galaxies that you move through time, but you have some method issues.
Okay.
So really, you want to compare the two.
Good. Yeah. Good.
Okay. So basically, the data that I'm using for this study is the MaNGA sample. The MaNGA sample provides us with spectroscopic information over the entire galaxy of 10,000 galaxies now. It's a very large sample, and this allows us to do more detailed studies of the other properties. You can divide the sample into beams of different properties, and you still have statistical significance in order to get the properties.
Okay.
So the MaNGA survey is pretty famous. It's one of the Sloan Digital Sky Survey projects.
Yep.
It was recently completed. Now we're moving into Sloan SDSS-5, which is the Milky Way mapper, and all the stuff. And basically, the reduction is really the key part, because if you don't get it well done, it's when things start to go wrong. In fact, we can talk about this more in the appendix.
Okay.
We used this Pipe3D pipeline, which is an analysis pipeline that takes the reduced data from the MaNGA sample and then fits the stellar spectra and the gas spectra, separates them, and gives you all the properties related to the gas phase, which we're not really going to use here.
Right.
And then when you have the stellar spectra, it fits templates of known age and metallicity of the emission of a population of stars of those properties would have.
Okay.
When you look at the galaxy, as long as you're not resolving the population, as long as you have a good sampling of the AMF in each spectral element, you have the sum of the flux of all the populations of stars that are contained within.
Yes.
What we do is we take known spectra, so spectra of known populations that have a certain age and metallicity, and we do a fitting. So which of these, in which proportion do we need to match the spectra that we're observing? Yes. This gives us the weights, and we obtain the information of which populations of certain age and metallicity we have, and we can use this information to then obtain both the star forming history, and what we're focusing here is the chemical enrichment history. Okay. The metallicity that the galaxies have at each time.
I'm with you. Cool.
Okay. So once we have this, one key point of the article is it takes a lot to explain, because it's how to average these histories. Because what we're doing is we take the galaxies within beams, and then we take what is the average chemical enrichment history representative of this group of galaxies.
Okay.
And we run into a problem. That is that goes into the real world, and this MaNGA survey has a different redshift for each galaxy. When we put the galaxies into the same time scale, the histories do not cover the same time.
Yes.
Because if it's farther, we can't see it like 5 seconds ago. We are limited by how far they are on how much how much of the time period we cover.
Yes.
This is a problem because if we just do the averaging, galaxies that are anomalous but don't cover the whole of the whole temporal range can induce changes. If you go to figure 1.
Okay. Let's take a look at figure. Yeah. There we go. Okay.
Here, this illustrates the problem.
Okay.
If you have on the top left, you have 2 example schematic histories.
Okay.
And the one below doesn't reach the same time as the other one because it's farther away. If we just do the average of these 2, you have the right panel. And there's an artificial jump.
Yep.
I say, oh, galaxies got enriched very quickly in this period. And it's like, no, that's completely wrong.
Right.
This is not representative of what's happening. So we do something that is a bit tricky, but it gives a much better representation of what is happening, which is in the row below.
Okay.
Which is that first we shift the 2 histories.
Okay.
So that their most recent metallicity is the same, and we shift them so that they match the average.
Okay.
And then we completely average them. And this gives a history that is much more representative of these 2.
Yes, I'm with you.
And just in case anyone is wondering, we have tested the method, and if the time ranges are the same, it gives the exact same curve as a normal average would.
Great.
We're not inducing
signal.
New. Yeah.
Yeah. Okay, I'm with you. Good.
And maybe I should talk a little bit about the libraries that we use, the templates. Just kind of jumped over that. And one thing that is particularly useful for this work is that the templates that we used were composed of observational spectra. So it's not theoretical spectra of stars, it's observed stars, the stars. And these spectra were observed using the same instrument as the one that was used for the MaNGA sample.
Oh, very good.
So you observe the galaxy with a spectrometer and you feed spectra of stars that are observed with the same spectrometer.
Good. Takes away the 0 point.
There's a lot of instrument-related issues that just disappear immediately.
Right. Very good. Cool.
I think that's more or less enough about the method, no?
Yeah, sure.
Other data that we have in sample is we have a morphology catalog that's from Vázquez Mata, that it's a very detailed. We're based on a catalog that is classified individually by eye using images from several surveys and a lot of processing. It's very detailed, and we use this one to train neural network algorithm that classified the others and gave, on the average, it gives very reasonable predictions.
Right. So this is for the morphology. Right? Yeah. Okay.
And this is the distribution of galaxies on the morphology bins.
Okay.
Can have an article now with some machine learning stuff. All the buzzwords.
Yep. Indeed. Very cool.
I think now we can go to the results.
Okay, I'm with you. So far, so good. Chemical enrichment history. Let's take a look at figure 3.
Yes, this is like first nice result we have. These here are the average chemical enrichment histories of all galaxies in the MaNGA sample divided into mass beams.
Okay.
Specifically stellar mass beams.
Yes.
And the error is, it looks very small, but it's actually, that's the error determination because we use the bootstrapping of the sample. So the variance of the chemical histories is much larger than this error, but we're not comparing the distribution. We're comparing how well determined the average is.
Correct. Yep. Cool.
So even though the distributions are wider and they might overlap, on average, galaxies of a certain stellar mass, within a stellar mass, are significantly above or below the other mass beam with this error.
Cool.
It's something that it bears mentioning because someone might see this, oh, the distribution of metallicities are so narrow, all galaxies evolve so similarly. It's not like that.
Right.
The distribution is wider, but their average is consistently like this.
Small relative to spread. Very cool. Good.
And
well defined.
What we see here, on the lower panel, we see the star forming histories. What we see here basically is that more massive galaxies are more metallic at all times, on average.
Yeah.
And they reach those metallicities before the less massive ones.
Yes.
Which is already good news. This is what we would expect. This looks nice and clean. This nice progression where from the more massive to the less massive, the slope changes such that the less massive ones are still getting enriched because they're still evolving.
Yes. That's our blues. Yes.
And this evolves similarly to the star forming history, in which galaxies used to be forming more stars, and the more massive ones just fell completely, whereas the less massive ones are more sustained in the star formation on average.
Misers. Yep.
And what we have here is basically the metallicity over time with stellar mass. We can switch these ingredients around and we get the evolution over cosmic time of the mass metallicity relation.
Okay.
Which is one of those key, super important relations in galaxy evolution and galaxy studies.
Yes.
And now we can trace it, how it evolves backwards to time. That's figure 4.
Let's get figure 4. Let's blow that up a little bit. There we go.
And this same information, different format. Now we still have the metallicity on the y-axis, but now the x-axis is mass. It's the stellar mass of the galaxies. And in colors we have times. It's look-back times.
Yes.
So the higher the number, the farther away, the more close to the beginning of the universe.
Yes.
And you see a shift, a change in shape, such that the more massive galaxies quickly reach their current value of metallicity. At the right end, they quickly reach there.
Yes.
But the low massive ones still haven't become enriched. And as time goes by, the low massive ones sort of catch up to their current value of the metallicity.
Eventually they get there.
This shows kind of the same that we saw in the other figure. The more massive galaxies are always more massive because they have this positive flow.
Yes.
And they become enriched earlier. They have a quicker evolution to reach their current state.
Cool. Yep.
And in the top panel, I show the distribution of the masses over the distribution of galaxies over the mass range. And you see the reason why the error grows at the low masses is because we have very few objects there.
Yeah. Yeah, we just don't have a lot of sample.
Exactly.
Cool.
But this is like the basic, like, important result. But now, as I said, I'm interested in finding what are the key processes, how different properties of the galaxy affect how it evolves, and specifically how it evolves in terms of its chemistry. So now we're going to start to divide the sample further, not only in mass, but in other properties such as morphology and star formation rate.
Okay.
Whether they start forming or not.
I'm ready.
Let's go.
Very cool.
Sorry. Before we go.
Okay.
One thing I want to mention in the mass-metallicity relation.
Mm-hmm.
You can probably see here, it's very clear the high mass flattening of the mass-metallicity relation.
Mm-hmm.
Flattened. It also shows that it becomes flatter over time. So it's already flat long ago, but as galaxies reach their current metallicity, they become a little bit more, from the green to the blue lines.
Yes. Mm-hmm.
Flattens even more.
Yeah.
And it's a little harder to see, but below like 9.7 in log mass, there's also a low mass flattening. Becomes a little flatter, especially.
Yeah. Okay.
It's kind of small, but we're going to talk more about this later. Just keep it in mind.
I will keep it in mind.
Now we can go on.
Okay. Mm-hmm. 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 Yep. Here, yeah. We talked about this here. This is the lower part. Okay. Good. Ooh.
Yeah. This is a more complicated figure. Here, we're trying to see the effect that morphology has on how the galaxies evolve.
Yeah.
And because we don't want to be like contaminated, so to speak, by the mass morphology relation, we just repeat the same figure as the first one, figure 3, but within different morphology bins.
Yes.
So have mass and morphology inside it.
Yes.
And lots of lines here, so let's go one by one. In each panel, you have in solid lines the chemical enrichment histories of that mass and that morphology. The dotted lines are the chemical enrichment histories of that mass, but for this whole sample. This allows you to see how they change.
The delta.
Yeah, exactly. With respect to the full sample. Okay. And in the bottom left, the shaded areas are sort of the representative error, because it would be excessively cluttered if I just painted again the shaded areas. Okay. So it gives you an idea of the error. Yeah. Sort of the average error over time. And what you should focus on here is that at a given mass, so no effects due to mass, same mass of galaxies, earlier type galaxies have more metallicity at all times, and they become enriched faster than late type galaxies. Yes, I see that. Okay. You see in the ellipticals, the blue and purple ones, which are the low mass galaxies, are still pretty flat evolution. They reached their current metallicity fairly long ago, and they are above the dotted line. But if you follow these two over the other morphology bins, they become lower metallicity and steeper, which means they're still becoming enriched. Yes. For example, in E2 and SC, for example. Exactly. They go from being above the full sample to being below the full sample, and from being flatter than the full sample to being more steeper than the full sample. Gotcha. Yes, I see that. And this, we'll see this even more when we look at the same, but with the mass metallicity relation with morphology, is one of the key results for me, what I like most about this article, is the fact that morphology is at least as important as mass in order to determine how a galaxy evolves. Okay. Mass is like the darling of the evolution of galaxies. Everything scales with mass. Sure. And many of those correlations are actually secondary correlations, like the bigger things are bigger, and you have more mass, you have more gas, you have more this, you have more everything.
which also spin it
And
fast.
in this case, we can go to the mass morphology, where we'll also see this again. Is that you can't ignore the morphology.
Right. Yeah. Cool. This is like
so once again, this is the mass morphology evolution for different morphology bins. No, sorry, what did I say? They say mass metallicity or mass morphology. No, it's the mass metallicity relation evolution.
Correct.
For different morphology bins.
It's like figure 2.
Exactly. It's figure 4, I think. The first 2 were about the method.
Oh, yeah.
The second results figure.
Correct.
Once again, you see here that from the early types to the late types, the slope of the mass metallicity relation becomes shallower.
Yes.
To the point that in SD galaxies, which include the irregulars, it kind of inverts.
Yeah, it goes down.
Which is, but you also see in the others, it gets flatter. And not only that, the timing in which the most massive galaxies have already enriched and the least massive galaxies still haven't, also changes. So that the delay changes. For example, you see in the ellipticals, the green line, which is sort of the intermediate time, where the most massive galaxies are already enriched, but the least massive galaxies still aren't. Yes. In the full sample, the low mass galaxies were not enriched, but here the ellipticals are already kind of enriched. They're in the middle already. Yeah. And as you go, the most massive galaxies at this time cease to be enriched. They're still not at their current metallicity. Peak. It's delayed. Late type galaxies have a delayed evolution in their chemical enrichment.
Okay. That's important.
Not only that, but mass becomes less important for later morphological types. Because if the slope of the mass metallicity relation becomes flat, it means that it doesn't matter what mass it is, galaxies get enriched the same way, the same amount.
Right.
And this, again, reinforces even more, you can't ignore morphology when you study galaxy evolution. And it's particularly interesting to me because this morphology is not the morphology at each time. It's current morphology. I don't have a way to measure the morphology in past times using this method. And there are studies from Consalice and many people that show that the current morphology scheme doesn't really hold up so well when you start to go to old times.
Yeah.
You start to have maybe spheroidals and disc-like, and that's it. And they switch between them. But whatever determines that a galaxy will end up in a particular morphology bin also determines its chemical enrichment history, which is a more powerful result to me.
Yes.
There's something underlying there that drives both of these things.
Okay.
Because many of these galaxies that are in these morphology bins, 10 gigayears ago, they were not in those morphology bins.
Yes, they have evolved.
Not necessarily, but they still follow the same evolution of other galaxies that end up in the same place.
Okay. A little degeneracy then.
Okay, so, and now for the next figure, where we're gonna see is similar comparison, but now we're gonna check what happens if we divide the sample, depending on whether they're currently forming stars or not.
Yes.
So these are star-forming retard and Green Valley galaxies today, and they're classified using the H-alpha equivalent width. So it's not even something that the code that analyzes this knows. The spectral fitting of the templates blind to this.
Okay, yes.
And again, most of the retard galaxies today were at some point star-forming, at least.
Already.
Otherwise, they don't exist.
Yes.
And yet, we see different evolutions. Retard galaxies are higher metallicity, and they have flatter evolutions.
Yes.
compared to star-forming galaxies, which are still becoming enriched because they're still forming stars,
Later.
and are generally a little bit lower in their metallicity.
Interesting.
And again, this is how they are currently, but they have differences in the past.
Yep.
When maybe most of the retired galaxies were star-forming. But whatever determines that the galaxy, whether a galaxy will in the future, which is our present, still be star-forming, or will it be retired, changes its chemical enrichment history.
Yeah.
Which really gives you important clues to determine what those processes are.
Yes, it does. Very cool. Okay.
And if we look at the mass metallicity relation evolution for these star-forming or retired galaxies, we can go back to the thing I promised you that you need to keep in mind about the flattenings of the mass metallicity relation.
Yes, I remember.
Let's go figure 8.
Figure 8, effective radial distance. Oh, mass.
Okay. No, that's later.
Yeah, it's later.
So this is the same thing. Retired green valley star-forming galaxies classified today. What is the evolution of their mass metallicity relation?
Right.
And similar things. Retired galaxies are more metallic, and they became enriched quicker compared to star-forming galaxies. See, with the intermediate 5.1 gigayear age, most of the retired galaxies at high mass have already become enriched, but the star-forming ones are still not. So similar, there's also a correlation between the morphology and whether it's retired or star-forming galaxy. So the new thing in this figure is with the flattenings.
Okay.
Because the high mass flattening appears very strongly on the retired galaxies, a little bit on the green valley ones, not at all in the star-forming ones.
No, still going.
Conversely, the low mass flattening, which was, you could see it, but kind of, it's very strong in the star-forming galaxies. Now you see it clearly.
Yeah.
It's completely absent in retired galaxies.
Yep. Up we go. Low and slow, high and fast.
So something's happening here. And for example, the high mass flattening has been linked to outflows and other mechanisms or AGNs, just removing metals from the galaxies.
Yeah.
And this fits that picture, for example. If you have like a galaxy being shut off by AGN or outflows, removing the gas, and that produces the flattening, the fact that you see it strongly in retired galaxies, a little bit in green valley, not at all in star-forming galaxies, fits this picture.
Yeah.
I have no idea what's going on with the low flattening, with the low mass flattening. It's just a bit weird. I don't understand it because it shows that star-forming low mass galaxies are more metallic than you would expect.
Yeah.
For their mass.
True. Relative to the.
Exactly.
So maybe they have some other outflow mechanism, right?
Yes, maybe the outflows are removing like gas that is low metal, so increasing the yield.
Yes. So like
it's something interesting. I want to pursue this a little bit more if I can.
Okay. Yeah.
So many things,
for example, you've got a low gravitational potential well isn't that deep. So you can maybe blow it out with supernova or something. Anyway, I'm getting in the way here.
No. Okay. And now we can check a different thing. So far we're just dividing the sample into different bits.
Yep.
But now we're going to take advantage of the fact that in these IFU surveys, you have information over the entire galaxy. So far, I've given the representative evolution of the whole galaxy.
Oh, you've got enough resolution.
Taken using the effective radius.
Yeah.
But we have the information to measure it at the center of the galaxy and at the outskirts. And see how that changes things.
Okay.
Do galaxies evolve similarly independently of the radius? Spoiler alert, no. So here, again, I'm showing you the solid lines are the chemical enrichment histories
Yes.
at that position of the galaxy. Average for all the galaxies, we measure at the position.
Yeah.
And the dotted lines are at the effective radius, which is what we've shown so far, which is like a proxy for the whole galaxy.
Right. Mm-hmm.
And interestingly,
Yeah.
things become more pronounced at the center.
Yeah.
The differences become stronger between the mass beams.
Yes.
The low mass galaxies are steeper than the are and the effective radius, and the more massive galaxies are more metallic, but at the outskirts, they're kind of similar. They're still segregated in the amount of metallicity, which is still less. This narrower, the range is narrower, which means that they are more similar in how much they become enriched. But they are also very, very similar in how quickly they become enriched. They're parallel to that. And this produces an interesting effect, which is shown in the right panel, when we plot the difference between these two. And we see that for the low mass galaxies, the two lowest mass beams, there's an inversion. The metallicity gradient switches from being higher at the outskirts of metallicity to being higher at the center. Currently, all galaxies are more metallic at the center than the outskirts. On average, this is well known and understood. But what this is suggesting is that the low mass galaxies didn't start that way. They started becoming enriched more outside and then switched to inside. Right. And there's some simulations and some data that has already pointed in this direction. The galaxies, low mass galaxies, like start forming stars mainly at the outskirts, and then there's like a differential quenching that pushes the star formation toward the center. Okay. And this is like excellent evidence for that, but it needs more work. Like, I don't dare do a very strong claim here, but it's really interesting. It is very interesting. Because you can even see that the intermediate mass beam, the 10 to the 10 to the 10 to the 10.5, reddish. It might, in the difference, it might have switched at a time we don't resolve with our method. Right, early on, Like it kind of touches the zero, that is like a flat gradient. And then there's this segregation over time where the less massive a galaxy is, the more time it takes for it to invert its gradient. Yeah. Okay. Which is outside in. Interesting. And figure 10 is like, doesn't really give you much more information, but it's similar. Center, more metallic. Everything is more pronounced. The flattenings are higher, especially the low mass flattening is more pronounced at the center. Yep. And on the outskirts, things are more similar and lower metallicity. Now, there's a switch for that. Interesting. Okay. And the next result is, I promise, the last one. I crammed a lot of results in this paper. So, when I do the average of the chemical enrichment histories, there's certain information that I'm losing. I'm just taking the average. I'm not how the histories are distributed, how they differ from each other, is lost. I can get the variance, like the width of the distribution, but I wanted to check something a bit more complex, which is in which way are galaxies similar in their chemical enrichment histories. And this diagram I showed the difference of the two things that I'm trying to separate. Okay. Is the variance originating from the fact that they have different shapes? Yeah. That they, for example, these are two histories where they would reach a very similar metallicity value today, but they are very different in how quickly they reach their current metallicity. Right. So they differ much more in terms of how they become enriched. Right. On the right panel, I show the opposite. So two galaxies that have very different values of metallicity, but they evolve in parallel. Yes. They become enriched at the same rate, as quick. And what I did is, okay, I measured these two differences, right? And I could do this taking advantage of that. You remember that averaging technique that was a bit weird?
It was a little different.
Because we do it in two steps. First, we scale them.
Yes.
And then we average them.
Yes.
Which means we can measure the width of the distribution in terms of the separation, and then the width of the distribution that is left after you put them together.
And
so these are two different distribution widths, different dispersions of the distribution.
There you go. Yep.
And so let's compare how galaxies of different mass, morphology, star forming, and forming status, how they are similar or different between each other. And that's the next figure.
Correct. I'm with you, because yeah, we have a little funky averaging there. Ooh, okay.
Yeah, the funky average is more useful than okay. So this is a very abstract figure. It takes a bit to understand it. What I'm showing is the two values. The sigma scale, which is how different are galaxies within a bin in terms of their final, their current metallicity value.
Yes.
And the sigma shape, which is how different they are in terms of how quickly they become enriched.
Okay.
And in the full sample, like for each x-axis tick is a different bin. The full sample shows in both of these parameters, less massive galaxies are more diverse. They have higher values of the dispersion. Yes. They are more different.
Yes.
The more massive galaxies are, the more similar they are in terms of what metallicity they reach and how quickly they reach it. They are more uniform. The chemical registers are more similar.
Yes.
Less massive galaxies have more, let's say, freedom. They can do whatever they want.
Small, flexible.
If we then divide this into the morphology and star-forming status bins, in general, this still applies. The more massive galaxies are more similar, lower values.
Yes.
You kind of see a correlation that for later types than SA, galaxies tend to be more different in terms of the metallicity value they reach. So it's flat, sort of flat for the early type galaxies. For the late type galaxies, it grows.
Yes.
But this is much more clear in terms of their shape. There is a nice increase, gradual, so that at the same mass, later type galaxies are more diverse in their evolution in terms of how quickly they reach their current metallicity.
Very nice. I like this plot.
Yeah, it takes a while to explain it because it's like the result of an analysis of an analysis. When I explain to people, it takes them like 5 minutes, right?
It takes a few minutes to go, but it's a nice plot.
Yeah. And really gives you information that I haven't really seen anywhere. It's like, how diverse are galaxies in their evolution? You get how they are, but not within the bins how diverse they are. And there are correlations. It's determined. And in the how star forming they are, in terms of the sigma scale, it's kind of funky. It's not very clear. In the shape, it does show, for the more massive galaxies especially, that star-forming galaxies are more diverse. Except the lowest mass bin is sort of flat. Like doesn't matter how star-forming I am.
Doesn't matter what you do.
I'm always different.
Yeah. There's just more freedom, more flexibility in those lower mass ones. Do what they're gonna do.
That's all of the main results. I don't know how we're doing in time, But
we're doing whatever we're doing. It's perfectly great. And there are 3 whomping appendices in this.
yes,
It's a 22-page article, and the main body is in the first 12 pages. And so sort of like the whole second half is all the appendices. And so Appendix A has an interesting one. Maybe you want to cover that?
yes. This is like a short but interesting one, because of one thing that we try to do is like, hey, MaNGA is a big survey, and it has a relatively large redshift range for a local survey. It goes, I think, from 0.01 to 0.15 in redshift, which might be enough to get a little bit of that evolution of the mass metallicity relation, just selecting galaxies at different redshifts. Like, we're going to do a cosmic survey.
There you go.
And spoiler alert, this doesn't work very well.
Oh, no.
No. The problem is how the sample was selected. MaNGA is selected by diameter, basically, and surface brightness.
Okay.
You want objects that fit nicely into your field of view of your instrument, and which are bright enough to get enough signal.
Yes.
This
Therefore
necessarily introduces a bias. In the top panel, I show a distribution on the 3 redshift values, that are 3 redshift pins, of the mass. And you see that the local galaxies are mostly low to intermediate mass, and it quickly starts shifting toward high mass as we go to higher redshifts.
Yeah, okay.
The higher redshift one is like only high mass.
Yeah.
Because you need bigger galaxies that are brighter, which means more gas, more mass, no solar mass. Can't avoid it.
I'm with you.
And that already gives you like the coverage is not the same. Like the oldest, the higher redshift one just covers just a tiny bit of the range in mass.
Yeah, right.
But well, maybe we can do something with the other ones, and you see a weird thing. Above, say, 9.7 in log mass, you see this growth in metallicity.
Yes.
The metallicity goes up a little bit, which is what you expect. But below that, there's this bizarre, weird shift in which they lower, they go lose metallicity on average over the entire sample, which is very weird until I started digging, and I found that because of the surface brightness selection, galaxies that are at higher redshift are more star-forming, because then they emit more gas. The emission lines are stronger.
Yes, okay.
Within this mass range, that there is this flattening and not flattening, so that the galaxies at the intermediate redshift are 2.4 times more star-forming on average than the galaxies at the local redshift. And it's not even a big redshift change. It's like from 0 to 0.003 and 0.003 to 0.1. It's we're not really going too far away, but already we're establishing a big bias. And why does this star-forming rate increase explain this? Because this, what we're seeing, is the star-forming galaxies low mass flattening. You remember that?
Yes, okay.
Mass metallicity relation for the star-forming galaxies, they have a strong low mass flattening.
Right.
At this mass range, the star-forming galaxies are at the intermediate redshift, and the non-star-forming galaxies are at the close redshift. So one is flattened, the other isn't. And if you assume that the sample is representative of both redshifts, you're interpreting it as a drop in metallicity, which is absolutely not what is happening.
Correct. Yeah, that's weird.
So this is more of a cautionary tale. Be very careful when you split your sample that you're not introducing biases based on how the original sample was selected.
Yeah, right. Good. Yep.
So I would not trust any paper that does redshift cuts in the MaNGA sample and doesn't at least do a whole lot of correcting these biases that we introduced.
Words of caution there. Yes. Very cool. Very nice. Good. Do you want to say anything about Appendix B or C?
Yeah, let's say Appendix B. The appendixes are like it's already a long article, and this is like the nitty-gritty. It's like getting a look at the bad stuff. I wanted to be as thorough as possible. This is what you're getting with the results. Be careful. This is where you can get things wrong. This is how much you can trust it.
Good.
So
like
in this figure, Appendix B is all about what the stellar libraries and how you construct them will affect the results.
Right.
Which is very important because it can have a very large effect.
Yes.
And this figure is, again, a little abstract. Basically, when we were doing this article, the library that we used was new. It was not constructed for this article, but it was recently made for the MaNGA sample for use on this type of studies. And we were testing things in terms of how to construct the library. More specifically in the time sampling, the age sampling of the space. Because, and this is a intrinsic unavoidable problem of stellar population synthesis, the older population is, the less accurately you can get its age.
That's true.
And the reason for this is because when you have a population of stars that is just born, the high mass stars dominate the emission. And you have a very, very steep, very blue spectrum. But these stars start to die very quickly. So as the age increases, the spectrum of the aggregate of this population changes very quickly. But as time passes, less and less stars die, and the spectrum changes less and less over time.
I'm with you.
You can distinguish between, so you can distinguish very well between 50 mega years ago and 100 mega years ago in a population, in the spectral population. Changes a lot. But if you try to distinguish between 10 giga years ago and 10.01 giga years ago, you're done.
You will never get that out.
Same. So you need to sample the templates that you give it in a way such that there are many more templates at low ages than at high ages.
Correct.
Because you're not going to distinguish any at the high ages. And here I'm showing several prescriptions. The first four are the same libraries as the ones in this article, but different age sampling. The last one, which is GSD, is here for comparison, because this is the library that was used in the previous version of this article, which was only the Khalifa survey. And GSD is a very established library for this kind of thing. And sort of to compare how well they do. So,
very good.
The colored little squares are the available templates. It's the ones that we have computed and they're available, and you select from these to construct your library. The color is how similar a spectrum is to the next ones.
Neighbor.
And it's basically the chi-square. You take a spectrum, another, and you take the chi-square. And as it becomes towards higher ages, the color gradient is showing you that they're way too similar. The chi-square grows because they're similar. They're the same thing, basically. But at low ages, the color shows that they are much more different. So you can get away with sampling it as much as we're sampling, which are the black dots.
Correct.
Each black dot is like, we selected this template. And this is why, if you look, the first four, each dot is centered on a square. But in the GSD one, it is not, because it doesn't draw from the same library.
Correct. It
doesn't have to match. Exactly.
In general won't.
First one is log. So log is the one that we use in the end. It's like a perfectioning of the log one. And it's like logarithmic sample, and then with a little bit more of old ages put in. Log is just logarithmic. Lin is linear, which is the worst one, because it's just like even sampling, which is terrible. And mix was an attempt that we made to get like the best of both worlds.
Correct.
It starts logarithmic,
Yes.
And then it gets linear.
Yes.
For high ages. So like, we got overconfident. Okay, let's get more old age sampling.
Exactly. So it's come to
that did not go well. You go to the next figures, you'll see the problems that start to appear because of this.
Okay. Cool. Let's take a look at some of those. There we go. Let's take a look at one. So
this is
okay.
Figure 3, but with what results from using different libraries.
Yep.
Slug is the same one, and the left is the same one we shown. It's very nice, has this growth, it's nice. Log is very similar, but it's kind of worse at old ages. You remember in the figure, Slug has a few more, just a couple more old age templates, and gives us this better precision. It's nicer at those, but it's very similar at the near, the loopback times that are near to us. It starts to get bad in the linear and mix, which are the ones that introduce too many
drafts.
Yes.
Yeah.
If you you give too many old age templates, those are too similar. The code can't somehow, I don't know the technicals, but somehow it gets confused. Like I can fit this one or this one, they're basically the same. And for some reason, this creates this artificial drop and growth and then drop again at the oldest stages.
Yeah.
Which is completely unphysical.
Correct.
Nothing. And the last one is the GSD one. And GSD has a certain disadvantage to the ones we're using, is the metallicity range.
Okay.
GSD has a narrower metallicity range. And consequently, things are mushed together. But what is very interesting and useful here is that it doesn't really saturate as much as you would expect. Like, it's not that, you can see this low range of metallicity and the galaxy should be here. Everything that should be below here is saturated at the lowest one. It still distinguishes between them.
Yes.
Not as well,
but
it still does. And this is a nice sanity check that even if you use a library that doesn't have an ideal metallicity coverage, you can still get qualitatively decent results.
Sure. Okay.
The differences between galaxies, you can still see them statistically. Quantitatively, not very good, but the conclusions are not bad, which is very good for me because this is what I used in the previous article. So I didn't say, okay,
right.
Previous article was completely wrong. No, this is not the conclusion. The previous article is okay. No problem with that.
Yes.
And the next figure is like the same thing with the mass metallicity relation. And again, somehow this weird low mass growths in metallicity start to appear.
Yeah.
And basically the conclusion here is be very careful about how you sample your libraries.
Correct.
You can introduce weird, unexpected results into the figures that you're producing.
Yeah, because these are all chi-squareds. So yeah, right.
And well, I hope it also serves as a validation of the results I'm showing. Like, okay, no, this is robust. This is we've tried different things. This is how it gets wrong. This is how it gets correct.
Great. Got it.
Yeah. And the last appendix is just I repeat the figures, but with the GSD library to compare directly to the previous article, which used Khalifa and the GSD library, which is a library that works best with Khalifa. And you get sort of the same conclusions, more or less, like the segregation in metallicity, that the more massive galaxies reach their core metallicity earlier. It's decently similar. You still see differences that are due to the instrument and the method.
Right.
So, but that super narrow error can be deceiving. You shouldn't take that as a, oh, this is how it is. This is method dependent, but within the same instrument,
yes,
same method, same libraries, the differences that you see are correct, are real.
Okay. Okay. Right.
It requires to keep in mind the problems of the method, but this is, I think it's a really powerful technique. We're basically taking a galaxy and looking backwards through time. Because in this galaxy, how was it 10 years ago? It was like this. And it kind of works.
It's impressive. Very cool. Great. Awesome. Very cool. So I'm going to let people, there's a lot of figures in this appendix.
Yeah. I think we need to go over this one because just.
Yeah, it's lovely detail. You should check it out. Very cool. Very cool. That's an awesome article. Artemi, thank you very much for walking us through the chemical evolution history of the MaNGA galaxies. Very good.
Thank you for letting me talk this long about it.
Yeah, it's all good. Let me ask, where do you think we go from here on this project? Is there additional SDSS observations coming? Is there additional wavelengths that could be done? Are there different stellar libraries coming on board that maybe one could use? Things along those lines. So kind of where does the community go? Let's say over the next couple of years on distinguishing this.
Well, obviously. The main new frontier in Galaxies is the same everywhere. Is James Webb. You can't. I don't know any talks you get with Galaxies. James Webb is going to appear. It's a word that's going to just show up because James Webb just lets you go further.
Yes.
And for example, in what I'm showing here, as I told you, the problem that the oldest populations, you can't resolve them.
Yes.
But if you have good observations at high redshift, you can fit the templates there. And when they're being observed, those populations are not as old. So they can be distinguished more easily.
Cool. Okay.
So that's something that I'm definitely interested in doing, which is when MIRI and NIRSPEC IFU observations start to come in, can we do this kind of thing and resolve the really, really old first stages of galaxy evolution?
Yeah, right. Cool. That'll be really awesome to see. Yeah. Well, I look forward to seeing that develop over the next couple of years. So
in the short time, I'm currently, it's gonna be submitted soon, but I'm doing some work on doing more detailed analysis of this. I actually have a paper in APG too, where I look at the chemical organism histories, and I noticed when I was studying them that some of them had like a drop, like they grow and they go down a little bit.
Okay.
And I wanted to see if that was just method error or is there something there?
Yeah.
And it appears that there's something there, that the at least on the average, this is measuring episodes where the metallicity in the galaxies was diluted.
Yeah.
In some way, like the metallicity actually went down because it correlates with the star formation rate of the galaxy.
Okay.
Such that the star forming galaxies, which have a drop, have a deeper drop. Which might be due to accretion of gas or outflows.
Cool.
And it also kind of appears to correlate with whether there's an IgN or not, which might produce an outflow that removes metals from the galaxy.
Nice.
So I'm currently trying to see how far I can push this method. Like, what is the most detailed analysis? I'm finding really interesting things. So if you're interested in this,
yeah, I'll put a link to that other paper in the description below this video. So very cool. Good. Artemi, thank you so much for your time and walking us through. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.